All right, taking a look at some application problems. Just as with the trig section on applications, the applications themselves are not new. They're just going to be in scenarios that involve either exponential or logarithmic functions. So our first problem says find the equation of a line normal to the curve, y equals ln of secant x, when x is pi over 4. Again, keep in mind that unless stated otherwise, that's going to be in radians. So we need the equation of a line. So that means we need a point and we need a slope. Now they gave us the x coordinate, pi over 4. So we can actually just go ahead and find the y coordinate. This doesn't require calculus. It just requires us to plug it in and give ourselves enough space to do so. So ln of secant pi over 4. Now secant of pi over 4, let's see, secant is the reciprocal of cosine. So cosine of pi over 4 is root 2 over 2, which means that secant is 2 over root 2. So I'm going to do this in the margins. Say cosine pi over 4 is root 2 over 2. So secant pi over 4 is 2 divided by root 2, and if you rationalize that denominator, you'll find that this is just equal to root 2. So this is ln of root 2. There's our y coordinate. You could approximate that in the calculator. That'd be fine to do. I'm going to just leave it as that in that exact form. So we have our point, pi over 4, ln of root 2. Now we need the slope, and that's where the calculus comes in. So our function is ln of secant pi over 4. Let's find dy dx. It's ln of some stuff, so that's my outer function. That means when I start taking the derivative, this is 1 over, oh, I wrote it as secant pi over 4, of course. It is ln of secant of x is my function. So when we start taking the derivative, it's 1 over the stuff, so 1 over secant of x times. Now let's see, the chain rule says I'm going to have to multiply by the derivative of secant x. So that's going to be secant x tan x. And then there's not really any more chain rule to apply because the derivative of the stuff inside secant is just 1. So I'll leave that factor off. We can simplify. We're going to cancel this factor of secant x. So dy dx is equal to tan x. That means that m tan, which is dy dx evaluated at pi over 4, is tan pi over 4, which is 1, and that means that the normal slope, because we wanted a normal line here, opposite and reciprocal is just -1. Now we have our slope, we have our point, so we're going to find the equation of the line. Y minus y1 equals m times x minus x1. So this is y minus ln root 2 is equal to -1 times x minus pi over 4. So there's the point slope form. We could get it into slope intercept form. There's -x plus pi over 4, and then add ln of root 2 to both sides. So it'd be -x plus pi over 4 plus ln root 2. And either of these is fine. It's also okay if you wanted to take this and approximate that in the calculator. Let's see, we would get pi over 4 plus ln of root 2 is about 1.132, and that's fine. All right, let's try another one. This problem asks us to find the area of the largest rectangle that can be inscribed in the first quadrant under the curve that they give us here, y equals e to the negative x. So they've graphed it for us. If they didn't provide a graph, if a graph was not provided for us, the first thing we would do is just sort of plug this in, plug the function into our calculator and just have kind of a sketch. Because I think in this problem it's helpful to visualize what they're asking us to find. So they're talking about inscribing a rectangle in the first quadrant under the curve. So I'm just going to draw a bunch of these different rectangles that could be inscribed. I'm going to erase them after because I don't want to have too busy a sketch to do my work with. But like here is one such rectangle. Here is another such rectangle. Here's another one. Right, here's another one. So these are all different rectangles. And basically what happens is one corner of the rectangle will be on the curve. The other corner will be the point 0, 0, right? And then depending on which point on the curve that we pick, determines the dimensions of the sides of the rectangle. So now I'm going to erase what I've drawn, and I'm just going to kind of draw a single rectangle here. All these rectangles that I drew, they all have like different areas. So what we're looking for is like, let's say it's like right here, right? I'm just drawing one. And imagine, I could sort of slide that point anywhere, right? So I'm just fixing it at I'm picking an arbitrary point. So let's say I pick the point where the x-coordinate is x and the y-coordinate, since it's on the curve, is e to the negative x. I could slide that point anywhere, I could draw all these different rectangles, and what I want to do is maximize that area. So one dimension, right, this length along the bottom, that's going to be x, that's the x-coordinate. The dimension, this other dimension, this vertical dimension, that is the y-coordinate, and in this case that is e to the negative x. So we want to maximize the area. Length times width is x times e to the negative x. There we have our function. This is an optimization problem. We've written our function area in terms of just a single variable x. That means we're ready to just jump in and take the derivative, because if we want to maximize or minimize something, what we want to do is find critical values. We want to take the derivative and figure out where the derivative is 0. And that's sort of how we get started with this. So a prime equals, using the product rule, g e to the negative x times f prime, the derivative of x is 1, plus f, which is x, the derivative of the second function will be e to the negative x times a negative 1. There's the chain rule. I'm going to simplify this a bit, e to the negative x minus x times e to the negative x. There's a prime. Now if I want to find critical values, if I want to know where this is equal to 0, I'm going to simplify, I'm going to factor out the e to the negative x. I could write it this way, or I could write it as 1 minus x divided by e to the x. Right, either way is fine, but I can see there's actually only one spot where this is going to be 0. There's only one critical value, because e to the x is never 0, and so e to the negative x is never 0. So that means that when I'm trying to figure out where my critical values are, I'm just looking at 1 minus x. So 1 minus x is 0. Clearly when x is equal to 1, we have a single critical value. Hopefully that's the one we're looking for that gives us a maximum. Now we have a couple ways to do this. Sometimes we find the second derivative and we check the concavity, right? It would be concave down at a maximum. In this case, I think it's actually easiest to just make a sign chart, because let's say I make a sign chart, like I'm thinking of the derivative in this form, right? So I'm going to make a row for 1 minus x and a row for e to the x. and then my last row just for A prime. There is a single critical value, and that is at 1. We know that e to the x is just always positive. 1 minus x, let's see, it's 0 there. If I plug in something less than 1, like if I plug in 0, we get a positive. So it's positive on the left. If I plug in something bigger than 1, we get a negative. And so for A prime, we have a positive, 0, and then it's negative on the other side. So that means that this does in fact give a maximum, right? It's increasing, it flattens out, and then it's decreasing. So it is in fact a maximum, and then we want to make sure that we answer the question. They didn't say find what x is to give us a maximum, they said find the maximum area. So we have one more thing to do before we're done. And that is just evaluate our area function. Area was x times e to the negative x. That's 1 times e to the negative 1, or 1 over e. That is the maximum area. You could approximate it if you like. .368. Okay.